this. There we go. All right, so first thing I want to do is tell you guys that apparently on the practical, some of the chapter 21 questions that I thought I had removed from the practical snuck their way in. I am waiting. I've got one person that is still taking the exam today, and as soon as everybody has taken it, then I will go in and give everybody credit for any of those chapter 21 questions that were on there. So you should see, if you had those questions and you got them wrong, you should see a change in your grade within the next few days for your lab practical. Are there any questions about the lab practical other than that? I will take the deafening silence as a no. Somebody speak so I know I can hear you guys. Anybody? Hello? Anybody there? Hang on, maybe I'm on mute. Speakers, headphones. Okay, try again. I have no sound. Faith, can you hear me? Oh, this is going to be one of those days. Is your computer on? Yeah, no, and I didn't think it was, but somebody try and say something now. Okay, hang on. Let me switch and try this. Okay, somebody say something now. I'm getting nothing. Why am I getting nothing from all of my places? Hang on, let's try. I don't understand what's happening. I'm not on mute. My computer's not on mute. Okay. Hang on. We're going to switch computers. Where's my other computer? Give me 1 second, guys. I don't know what's happening with that computer, but it doesn't want to work. So, which computer? I can't get the sound to work on the PC over here. No, can't get it to work.
Yeah, you have to make some adjustments to get the sound to work.
Apparently. All right, I'm gonna sign off here. Give me just a second, and I'll be right back, guys.
You try just checking your sound setup?
Yeah, it's just easier right now to load up the other computer. At least I think it is. Cancel. Come on, you can do it. Come on. Oh, no. Okay, now somebody talk to me.
Good afternoon.
Yay! I can hear people again. Okay, so does anybody have any questions about the practical other than the chapter 21 questions that weren't supposed to be there that you will get points back for?
No, I know it's kind of about the 21 questions, but do you know about how many there were?
I do not. I haven't gone to look yet.
Okay.
You would have known if you got them. You may not have gotten any. It's possible that you didn't get any because I thought I deleted all of them. But apparently a couple of them got stuck in there where they weren't supposed to be. Okay, so we are going to move into chapter 21. And you may have noticed that there is no lab material for chapter 21, which is why chapter 21 should not have been on your lab practical. You don't have any lab material this week. All you have is lecture material. So this is an opportunity for you guys to really focus, get caught up on some things, and kind of breathe a little bit. So I'm going to pop through these slides just like normal, and you should let me know when you have something that you need me to talk about. Any questions here? Okay. You guys understand? Hang on a second. I do. Okay. So one of the things that you're going to notice is we're going to talk a lot about the size of vessels. For instance, here they mention arterioles. So what you want to remember is that it kind of works in this general way. So the biggest artery in your body is the aorta. The aorta becomes smaller, like medium to large to medium size arteries. Arteries become arterioles. And arterioles feed into capillary beds. Okay. From the capillary beds, we go out to venules, which are the smallest veins, and then we go to large and medium size veins, and the largest two veins in the body are the superior and inferior vena cavas. Okay, does that make sense? And then, of course, the heart is in between. Okay, so this is how your circulatory, this is actually one of those things. So we call this your circulatory system, right? But when we talked about systems in A&P 1, I told you there were 12 systems, right? Circulatory was not one of them. Okay, this is not one of the systems like the nervous system and like the cardiovascular system and like the urinary system. This is a system that actually combines both the respiratory system and the cardiovascular system. It is the connection between those two. Okay, so I want you to think of it as a system, but not like one of the major systems in the body. Does that make sense? Okay, cool. All right. So we're going to move forward. This pathway, by the way, if you keep this in mind, this will make your life easier in a lot of ways as we move forward. I want to talk about this here. Yeah. All right, moving forward. Capillaries. Anybody have questions about this slide in regards to capillaries? What does this word mean?
It reminds me of the perifollicular cells. That it's like in between.
So in between what?
In between cells?
Sort of. So think of this more in terms of things like the pericardium or the periosteum, right? That was sort of around the outside of the bone or around the outside of the heart. Pericapillary cells are cells that are on the outside of the capillary, okay? They're underneath of the basement membrane, which is what this sort of fuzzy pink is that you see here. So they're on top of the capillary wall, but sandwiched in between the basement membrane, which attaches that capillary to things, and the capillary itself. Does that make sense? Anybody confused by that? Okay. Questions about types of capillaries? There's these two. Do you understand the differences between them? And then there's this one. Go ahead. Is somebody speaking or is somebody just not on mute? I think that was somebody not on mute. Okay, I'm going to assume you guys are good with this and move forward. Questions here?
Can you go over like the flow throughout the diagram? Like what directions?
So again, this is sort of what we just talked about, right? So you've got this meta-arterial, right? So you've got your arterial, that's the little tiny guy, right? And then, blow that up a little bit. There we go. Is that better? Okay. I see you guys start to lean in like you're trying to see. So this arterial, which is the smallest one we talked about, branches off into these meta-arterials, okay? And meta-arterials are just sort of the beginnings of a capillary bed, okay? Now, that blood will pass through, okay? It will pass through this thoroughfare channel that basically, oh, wrong color. Let's try a different color. That goes directly from arterial to venial, okay? So it can pass directly through. Or that blood can be sort of sent off and branched out and sent out to the capillary beds. Can anybody look at this figure and tell me what it is that might be, oh, the word's not on here, but if you could describe for me where in this picture you see something that might control whether or not blood is leaving the thoroughfare channel and going out into the capillary or not. Oh, actually, it is labeled on here.
Isn't the sphincters?
The precapillary sphincters, right? So there's one on each branch off of the thoroughfare channels. Okay? If they are open, then blood that is leaving this arteriole will go out into these capillaries. If they are closed, then that blood will go straight through that thoroughfare channel back into the venule. Okay? Does that make sense? So based on this picture, where would you expect if I were to turn this, so let's say we turn this picture. Hang on. I'll try to make this a little easier. Which end of this did the blood start on? Did it start on the right side or the left side? So we'll say this is for purposes while we're staring at it. This is going to be the right side. This is going to be the left side. Okay? So did the blood start out at the very beginning of this process? In other words, did it come from the heart, from the right side or the left side of this picture?
The right side.
The right side, because these are the arterioles up here, right? And the blood is traveling that way. Okay? So basically the blood from the heart has come through all of those arteries down into the arterioles, and then it will go through here, and basically the purpose of capillaries in general. Anybody know what the big purpose of a capillary is? If you could say it, it's 2 words.
Gas exchange?
Say that again?
Gas exchange?
Yes. Gas exchange. That is the goal of capillaries. Well, nutrient exchange, anything exchange, but gas exchange is primarily what we're thinking about right now, okay? So oxygenated blood comes into the arteriole, it goes through these capillaries, and you can see that as it passes through the capillaries, it gives up its oxygen and picks up carbon dioxide, and then it goes back to the heart. You guys with me? Is this making sense? Okay. All right. Moving forward. Okay. So, this is an arteriovenous anastomosis. First of all, somebody describe for me in easy terms what this is.
A connection.
It is a connection between what?
Arterioles and small veins.
Yes, it's the connection between the arterioles and the venules. And what is important about it? Why is it important? Why are we talking about it? What's
It's a direct pathway.
It's a direct pathway that allows us to skip what?
Capillaries.
Yes. So basically what this allows for is, all of this stuff is happening, and oh crap, I need to get the blood back up quickly. I don't have time for it to all go through the capillary bed. I need to pull it back in because something is happening. I need to warm the body. I'm having some sort of issue where I need to run away and I need to move that blood to someplace else. It allows for me to change the direction of blood flow fairly quickly. Now, we talked about something else. So we're going from arterial to venule, and we're skipping the capillaries, and we're skipping the heart in this process. What else did we talk about this semester that took blood from one place to the other but didn't go through the heart, but actually instead went through a capillary? I went from one capillary bed to another
The
capillary.
hypophyseal portal?
Yes, the hypothalamo-hypophyseal portal system. So what is the difference between a portal system and an anastomosis? This is the
Is the direction?
It's not necessarily the direction, because this could be, I mean, it's generally speaking going to be oxygenated blood going to another place. But there's a major difference. So with the hypothalamo-hypophyseal portal system, I start in a capillary bed and I end in a capillary bed. How is that different than the anastomosis?
Starts with an arterial and ends in a venule.
And skips
The capillary.
the capillary, right? So both of these are ways to move blood quickly from one place to the next and to accomplish a process, but they are different in terms of how they make use of capillaries. Okay? I just wanted to sort of help you make that connection. Does that make sense? Okay. So, move forward. We're going to sort of talk very quickly, very high level about these different kinds of veins, right? I'm not really going to ask you a lot of detail about the tunicas. The tunicas are basically just layers, okay? So each vein, as you get larger, has an additional layer that makes it a little bit thicker, okay? And a different number of layers, and the layers are slightly differently arranged, and there's quite a bit of variation in them, and I'm not going to ask you to know all the details about this. All you really need to know is that the large veins are going to go to the medium veins go to the small veins go to the venules, and the venules come from, sorry, going the wrong way with this. They come from. Why did I change that? Why did I say come from instead of go to?
The arterioles connect to the venules.
Well, do they?
They can.
Well, they can if I have an anastomosis, but most of the time, what connects directly to the venules?
Capillaries.
Yes, the capillary beds. So the capillary beds feed the venules. And then the venules feed the small veins feed the medium veins, the medium veins feed the large veins, and then eventually we end up back in the heart. Does that make sense? Yeah? Okay, so we talked about valves in the heart, and now we're going to talk about valves in the veins. Okay? You will find valves in all of the veins that are bigger than 2 millimeters in diameter. Now, why would I need valves in veins, but not necessarily in arteries?
Veins are going back up to the heart.
Veins are going back up to the heart. So think about, first of all, what do you think is driving the movement of the blood through the vessels? What is the primary driver in the movement of blood through the vessels?
The heart.
Blood pressure?
The heart, right? The amount of pressure that was exerted. So if that's the case, as blood moves farther away from the heart, what is going to happen to the speed at which it is traveling?
Doesn't that depend on if it's going up or down and gravity and all that?
Well, so we're talking primarily about the body. We're not talking about necessarily the head, because you're not going to find veins with valves in the head. They're not big enough.
It will slow down.
It will slow down, right? So the speed of the blood is going to decrease as it gets farther and farther away from the heart into the body, right? When the blood gets down to your feet, it is moving at a very slow pace comparatively to the way it was moving when it left the aorta. Now, here's the problem. I've slowed down, and now I've got to go back up against gravity. Okay? So I have these valves that allow for a little bit of help, right? So as the blood passes through here, if it slows down too much and starts to come back, it will be caught by these valves, and so it won't be able to come back as far. Now, what do you think we could possibly use maybe in our legs to help sort of move the blood along and get it back up out of the lower body towards the heart? Do we have anything else that we could use?
Elevate them.
Well, yes. So elevation will help, but if I don't, I mean, I can't spend all day sitting around elevating my feet, but blood is not pooling in my feet all day long, right? So how is it getting up on a regular basis during the day?
Exercise, maybe?
Well, walking in general, moving. They call it the skeletal muscle pump. So if you think about the muscles in your legs, every time you walk, every time you take a step, those muscles contract. And in contracting, they also help squeeze that vein to help move that blood. It's why they will tell you after you have leg surgery or any kind of serious knee surgery that one of the things they want you doing is they want you pumping your ankles. So basically moving your feet back and forth like you would if there was a pedal, so that you're using those calf muscles to help move that blood to keep them from pooling. It's also why they tell you that if you fly long distance, like over the Atlantic, that you should not spend the entire trip sitting down, that you should get up and move around, because the blood will actually pool if you don't. Fun facts. Questions? No? Okay. Moving on. All right, so we've already talked about portal veins, right? We talked about portal veins in terms of the hypothalamo-hypophyseal portal system, but there are other portal veins in the body. One of the big ones is the portal system that is the hepatic portal system. So you have capillary beds in the liver, and you have capillary beds in the stomach, and in the pancreas, and in other places. And that portal vein basically allows for blood to travel between these capillary beds without going back to the heart first. Okay? The liver does a good amount of filtering of the blood and sort of helps determine where a lot of those nutrients go. So all of that has to go to the liver. And then from the liver, it will intersect with these capillary beds from the venous system, and it will be sent back up into the superior and inferior vena cavas. Does that make sense? Anybody have questions? So the vasa vasorum are blood vessels that actually supply tissues of the arteries and the veins. Okay, so just like the heart muscle has to have vessels delivering blood to it, so do the major arteries and veins, because they're too thick to use the blood that's flowing through them. They have to have their own blood vessels. So vasa vasorum, the vessels of the blood. The vessels of the vessels, actually. Does that make sense? Yeah, okay. Moving on. The differences between arteriosclerosis and atherosclerosis. Any questions here?
Can you describe those more in depth?
Really, all you need to know about them is that one is a natural process that happens that you have no control over, and the other one you do have control over to some degree. So arteriosclerosis is a natural occurrence that as you get older, the arteries become less elastic. And when the arteries become less elastic, they start to slow down. They don't function as well. And so that is something that you can't really prevent. Arteriosclerosis is sort of a natural degenerative effect that happens as you get older. It's why heart disease and heart issues increase with age. Atherosclerosis is the deposition of plaque on the walls. So this is your atherosclerotic, color that I can see here, your atherosclerotic plaque that's sort of building up in between in the walls of this artery. And what happens as a result of this is that the amount of space in the artery for blood to travel gets much smaller. And when it gets much smaller, everything slows down, and eventually you can end up with blood clots and other issues that will lead to a heart attack. Does that make sense? Yep. Questions about the hepatic portal system? Questions? Okay, moving on to the second PowerPoint of chapter 21. Okay, so now we're talking about the dynamics of blood circulation. And this is all about flow, resistance, and pressure. We've been talking about some of this already as we talked about the cardiovascular system. Can you close that door?
Sure.
My maintenance guy is mowing the lawn. Not going to help a great deal, but it will help some. Yeah, no, it doesn't help a great deal, but it will help some. Okay, sorry about the buzzing in the background. So, I'm going to assume you guys don't have questions about the, like, 12 words that are on this slide. But if you do, feel free to ask them. Okay, moving forward. All right, questions about laminar and turbulent flow.
Maybe the air conditioning will grab that weird lawnmower.
No questions about this? Everybody's good here?
Can you go over the differences, please?
So the differences are basically how the blood is moving through this process, right? So in laminar flow, the blood is all moving in a very streamlined, orderly fashion, right? It's a nice straight line. Everybody is moving in the same direction. Nobody's sort of turning around and trying to go upstream. Think about it in terms of if you've ever gotten on an escalator in like an airport when it's really busy, right? Laminar flow is what happens when everybody is moving in the right direction and everybody gets on the escalator and everybody moves nice and slow and smoothly in one direction. And nobody tries to create any chaos and turn around and do anything goofy, right? Everybody moves quickly. Everybody moves nicely. Traffic is a really good example of this. When you're driving in traffic and you have a place where you have to merge and everybody is sort of nicely zipper merging and letting cars go in where they're supposed to be, and there's no stopping, there's no slowing down of the process. Everything is moving in one direction in an orderly manner. Okay? Now, when you have laminar flow, the fastest blood is going to be in the center of the vessel because it is going to have less resistance, right? The blood that's on the outer wall is dealing with more resistance because it's got that wall that it's working with. Does that make sense?
Yes.
Okay. Guys, don't forget your cameras are supposed to be on. It's a little bit irritating when I'm looking at black screens and just names and I can't see faces. Okay, now turbulent flow. Same example. So let's imagine you're in a crowd of people and you're going up an escalator, and some crazy person decides halfway up the escalator that they need to turn around and go back down. What is that going to do to the movement of people as that person turns around and starts to go against traffic? What is that going to do to the flow of people?
It's going to disrupt it.
It's going to disrupt it, right? It's going to become chaos, and people are going to be pushing and bumping into each other, and nobody's going to be able to walk in a straight line, and it's just going to become chaos. And that is what happens when you have turbulent flow. And what's happened here is that the blood has started moving faster than it is normally capable of. And as it speeds up, it runs into a narrowing of a vessel. So lots of blood flowing in one direction, and all of a sudden the tube gets smaller, right? And so that's going to create a lot of friction, and that friction is going to cause a lot of sort of out of control movement, and it's going to slow everything down. Okay, so when you are listening to blood through veins, you're not normally going to hear turbulence in an artery. That is not a normal sound. You will know it when you hear it, but it's not a normal sound, and it's usually due to some kind of a narrowing or constriction of the vessels, and that could indicate the increased probability of a thrombosis, which is what? What is a thrombosis?
A platelet.
A what?
Is it a platelet?
A thrombocyte is a platelet. What is a thrombosis? Is a blood clot, right? So platelets, which are thrombocytes, cause thromboses, which are blood clots, or can cause. Does that make sense? You guys good with that? Okay.
I have a question. So these flows, are these regarding like all types of flows throughout blood vessels, like all types of blood vessels?
Yes. Yes.
Even with veins that have like the valves in it and all that?
Yes. So the valves, all the valves do is prevent backflow. So when blood is flowing properly and you've got the right blood pressure and everything is working the way it's supposed to be, then yes, you can get laminar flow. You're going to get more turbulent flow in veins where there's not enough pressure to keep the blood moving, where it keeps backing up into those valves and kind of having to get started again. You're going to see more turbulent flow there. Does that make sense? Okay, moving on. Questions here? No questions here?
Can you go over how flow is calculated?
Yeah, well, I'm not going to ask you to calculate flow, but basically all you're looking at is P1 minus P2 over R. Okay? So basically the starting pressure, the initial pressure, and the ending pressure over the resistance. I'm not going to make you calculate it. I'm not even going to ask you to know the calculation. It's just there because I want you to be able to see it and understand that there is a way to do it. They may ask you to do it in your nursing classes. This is not a calculation I'm going to ask you to worry about. Other questions about this slide?
Do we have to know the laws, like specifically for the exam?
You should know the laws, yes. And they're not complicated. There's a lot of words there, but this is an example. Okay? So if you read the information that describes the law, somebody read that and tell me in their own words what this law is. And I don't ask anybody to pronounce his name. I just call it Mr. P's law. My grandmother could probably have pronounced it because it looks French to me.
I just get that flow and resistance are inversely related.
Yeah. Yeah. So because flow is inversely related to resistance, so if flow decreases, sorry, I need to do that the other way. I always do this the other way. Hang on. So if resistance increases, then flow is going to decrease, right? Since that's the case, then if I constrict a vessel, so I go from having a big vessel and I constrict it and turn it into a smaller vessel, I have increased resistance and therefore decreased flow. So constricting a vessel decreases blood flow, basically is what this law says. Okay? Yes, you need to know which laws are telling you about what. Okay? This is just an example down here of how this law works in reality. Other questions? Okay. Questions about viscosity?
Can you explain like the difference between velocity and viscosity whenever
Okay.
like
So
keywords to remember?
viscosity will slow down velocity. Because if something is viscous, so think about it in terms of what is thicker, like heavy whipping cream or skim milk. Which one's thicker?
Heavy whipping cream.
Okay. Now, if you compare those two thicknesses to your blood, if your blood is more like skim milk, lots of water, just the appropriate amount of blood cells and other things in your blood, it's going to move faster or slower than if your blood is the thickness of heavy whipping cream with less water and more cells in there than is normal. Which one's going to move faster?
The thinner one.
The thinner one, right? So the speed at which we move is our velocity. How thick the liquid is its viscosity. Okay? So it says right here, I'm saying this loudly because there are people in my household that don't drink enough water. I'm one of them, but there are only 2 of us in this household. Dehydration or uncontrolled production of RBCs can lead to increased viscosity, which increases the workload on the heart. Why does that increase the workload on the heart?
It doesn't run so smoothly.
So think back to Wednesday's lecture. And we talked about something called cardiac output. And cardiac output was a combination of what?
Heart rate and stroke volume.
Okay. Now, cardiac output played a role in something else.
It was like the mean pressure.
Mean arterial pressure, right? Mean arterial pressure, cardiac output times what?
Peripheral resistance.
Peripheral resistance. We are talking about peripheral resistance here. As viscosity increases, peripheral resistance increases. If peripheral resistance increases, then our mean arterial pressure is going to increase because the heart has to work harder to get that blood to move where we need it to go because the resistance is higher. Does that make sense?
Can you explain what peripheral resistance, like in a situation, like how it would increase?
So this is
decrease.
what we were just, how it would decrease. Drink more water, your blood gets thinner, peripheral resistance goes down.
So it's good to have a peripheral resistance like low.
Well,
Okay.
it's good to have an appropriate peripheral. There's such a thing as too low, right? Right? So everything in moderation, everything in balance. But, you know, if you've got high blood pressure, a lot of the times what they're going to do is either try to find a way to relax the vessels or to reduce your blood volume. And very frequently, the reduction of the blood volume comes from reducing the amount of water in the body, which reduces the amount of water in the blood. So they give you a diuretic, you pee a lot of water out, you have less volume of blood. Makes it a little thicker, but there's less of it, so you kind of get that balance. Does that make sense? Peripheral
Is a stent a way to decrease PR?
Yes, because it will open up the vessel. Right? Because remember we talked about the size of the vessel, right? So as the blood's flowing through this vessel, it's flowing through this way. If this vessel narrows, then all of a sudden, this blood, the same quantity of blood that was out here, is going to have to work much harder through this smaller space. So if we use a stent to open up that vessel and help keep it open, then that blood will flow through much faster and much easier. Does that make sense? Okay. All right. On. What about this? How are we feeling here? Again, not going to ask you to calculate Laplace's law, but you should know what variables go into calculating it. Okay? And this is pretty straightforward. We've been talking about this. The force of the blood acting on a vessel, so how much force is being generated against the vessel wall, is proportional to how big the vessel is times the blood pressure. Okay, so how hard is the blood moving? How big is the vessel? Those two things together will tell you how much force is being put on the vessel wall. Why is that important?
Is it possible for too much force to collapse like a blood vessel?
Well, too much force is not likely to cause a collapse. Too much force is liable to cause a bursting, a blowing up of a blood vessel, tearing of it. Your critical closing pressure is a function of too little pressure. Okay? So what this is telling me is if I don't have enough pressure in a blood vessel, that vessel is likely to collapse And if that vessel collapses, then blood flow will stop. That is what critical closing pressure is. And Laplace's law is how you can sort of evaluate critical closing pressure. Does that make sense?
When a blood vessel dilates, the force increases, is what that equation can tell you, right?
So if the diameter of the vessel increases and the size of the amount of pressure stays the same, the force is likely to decrease. Because remember that pressure is going to be a percentage. So a bigger diameter times a smaller pressure times the same pressure, right? Because if I have a blood vessel of this diameter and a blood vessel of this diameter, and I have a pressure of, I don't know, 80 millimeters of mercury here and 80 millimeters of mercury here, this one is going to have less pressure than this one. Okay? Because remember, the force on the blood vessel, the force is proportional to diameter times pressure. So as diameter times pressure goes up, force goes down. Make sense?
I am working and Judy's teaching, so
You with me?
I'll call you back in about 20 minutes.
Yes, no, maybe?
Okay, bye.
Not so much. Let's see.
Okay, that last comment didn't make any sense to me, because if pressure goes up, why would the force not go up with it?
Because the diameter got bigger. Pressure stayed the same.
But if you have more in a bigger surface to cover, wouldn't you need more force to push it?
If volume goes down, pressure goes up. If volume goes up, pressure goes down, right?
Is force like tension on the wall?
Yes. Yes. Force is the amount of pressure being exerted by the blood pushing against the wall of the capillary. Okay? So think about this. I keep going back to this example, but it works really well. Think about it like a balloon, right? If I have a balloon and I have a little bit of water and a little bit of space, then I'm going to have a certain amount of pressure on the wall of that balloon. If I blow that balloon up, that water is going to exert less pressure on the wall of that balloon because the balloon got bigger. Does that make sense? Okay. All right. So we're getting there. Now, we have this vascular compliance issue. Is everybody understanding what compliance is and how this works? Anybody have questions about compliance? Compliance is just stretch. Okay? All right, moving forward then. Questions here. This is the graph that usually confuses people. Questions?
Can you go over it, please?
Okay, so what we're talking about here is if I were to measure the amount of area that each of these different blood vessel types takes up in your entire body, what you're going to find is that the bigger vessel takes up less cross-sectional area. Okay, so we have biggest to smallest, and then smallest to biggest, right? So we only have one aorta, right? So it, being the biggest artery in the body, takes up a very limited amount of space, cross-sectional area, right? But as I move smaller and smaller, I get more and more of these smaller vessels, right? You have to think about this in terms of whatever amount of blood the aorta carries, the arteries have to carry, the arterioles have to carry, and the capillaries have to carry. Because they are smaller, they need more of them in order to be able to move the same volume of blood. Does that make sense? Okay. What that also tells me is that the highest velocity of blood is going to be in my biggest vessels, because every time it has to go through a shrinking of size into the next vessel, it's going to slow down. Right? So your highest blood flow is going to be in the aorta. It's going to slow down almost all the way to 0 by the time it gets to the capillaries. And then thanks to things like the skeletal muscle pump, it will pick up a little bit of speed by the time it gets to the vena cavas. Does that make sense? So the smaller the vessel, the more cross-sectional area I have, but the slower my blood is going to move. Does that make sense? Okay. As compared to this. Okay. Velocity and blood flow are very much the same. Or velocity. Oops. Questions here?
Can you go over the graph?
Sure. So this is very similar to what we were just talking about, right? In terms of pressure and our arteries and veins. So natural pressure is highest in the aorta, okay? And what are we measuring here? At the top and at the bottom, we're measuring systolic and diastolic pressure, right? So less than 120/80. And as this blood moves out into the capillaries, both of those pressures, both your systolic and your diastolic pressures, are going to drop. And as I said, they're going to drop until they're very low. Okay? Now, they do pick up some speed down here. We're not really paying much attention to this because, like I said, nobody really cares how fast the blood is moving in your veins. They only care how fast it's moving in your arteries. Once it gets to the capillaries, that skeletal muscle pump will help move it back to the body, but it's no longer moving as a result of the heartbeat, right? It's not moving primarily as a result of that heartbeat. It's now moving because of the skeletal muscle pump. Does that make sense? This is just another way of looking at pressure. Pressure are very much related. Does that make sense? Yes? Okay. Pulses. Okay. Questions here? I am not going to ask you to identify locations for pressures.
Does pressure, like your pulse pressure, decrease with how far you get from your heart?
Yes. It will. Not significantly, but it will. Chloe?
So you said we don't need to know like the pressures, like the common carotid artery and all that, but like on our lab we had to like place like the fingers on where the pulses were and all that. Are you just saying for like test purposes?
Yes.
Like,
Yes.
gotcha.
So very frequently I will tell you there are things I'm not going to test you on that you're going to be exposed to in class or in lab. That exposure is just so that when you get to your nursing program, you've had some exposure to it, but it's not something I expect you to be able to retain here. Okay?
Okay, thank you.
All right. Capillary exchange and regulation of interstitial fluid volume. Questions here? No questions? Okay. Okay. Now, how many of you understand the difference between hydrostatic pressure and osmotic pressure?
Can you describe the relationship between them, like how they increase and decrease with each other?
Well, so it's not necessarily, so they're not necessarily going to increase or decrease in relationship to one another. They are going to work together or against one another in order to generate a net filtration pressure. So hydrostatic pressure is the physical amount of pressure of the fluid, of the blood or the fluid traveling through a space. So you can have a hydrostatic pressure inside of the vessel from the blood, and you can have a hydrostatic pressure from the fluid outside of the vessel, the interstitial fluid. Those two pressures will determine which direction certain fluids are going to move and will have some influence on osmotic pressure in terms of how the solutes are going to move. The osmotic pressure is talking about solutes, the things that are dissolved in the fluid. Okay? How much pressure is necessary to move solutes through a membrane when there are other proteins that do not move or cannot move across that membrane. This is something that's going to become really important to you when we get to the urinary system. I don't expect you to understand details of this right now, but I do want you to make sure that you understand the differences between them. Does that make sense? Okay. So, this is again what I was talking about with the, so if you've got a vessel, okay, you have your capillary hydrostatic pressure, which is the blood inside putting pressure on the vessel walls. You have your interstitial hydrostatic pressure on the outside putting pressure on the walls. Okay? Those forces are opposing one another. Okay? You also have blood colloid osmotic pressure, which is basically the amount of pressure that the solutes are putting are needing in order to move across the vessel wall, versus your interstitial fluid colloid osmotic pressure, ICOP, which is basically how much effort extracellular solutes have to put in order to move into the capillary. Okay, so this is all about our ability to move things across the capillary wall. Okay, and these pressures, net osmotic pressure and net hydrostatic pressure, they work together. So if I add these together, then I get my net filtration pressure, which tells me how successful am I being at filtering out what I want to out of the blood and keeping what I want to in the blood. You guys following me? I see very sort of statically confused faces. I can't tell if you're confused or not.
So the capillary hydrostatic pressure, is that blood being filtered out of the capillary?
No, that is the
It's
hydrostatic pressure is, well, in this case it is blood. Blood is the fluid, but it's not that the blood is being filtered out. It's that the blood is exerting pressure on the capillary wall. Okay? Now, very frequently what you will find is that water is going to be exchanged in a lot of these places. And that water is carried in the blood, right? So if I need to move, so let's say that in my interstitial fluid I have lots of water. I have high water here and I have low water here. Which of these two pressures needs to be higher in order for me to move water into the capillary?
The outside.
Right. The interstitial hydrostatic pressure needs to be higher than the capillary hydrostatic pressure in order to move water into the capillary. Okay? Does that make sense? That's all this is talking about, is that there's this balance, this relationship between them, and by changing one or the other, we can determine what's going to move where. This is going to, again, become really important for you when we get to the urinary system. Okay? This will come back to haunt you. So learn it now. It's less you'll have to learn when we get to the urinary system. Back here, I have net hydrostatic minus net osmotic equals net filtration. Okay. So, here's what we're looking at. Okay. My net filtration pressure is my net hydrostatic pressure minus my net osmotic pressure. Okay, so at the beginning of this capillary, at the arterial end, so we've gone from aorta to arteries to arterioles, and we are coming into a capillary. Okay, as that blood comes into the capillary, my hydrostatic pressure is 33 millimeters of mercury, and my osmotic pressure is 20 millimeters of mercury. Okay. Net filtration pressure is positive because the hydrostatic pressure is greater than the osmotic pressure. Okay. That means that fluid is going to move, wrong one, out. Okay, I can move things out of this capillary on the arterial end. Okay, we're going to lose about 9/10 of the fluid that leaves the capillary is going to come back in. Okay, so we're going to do this little loop-de-doo. Okay, and we're going to end up with most of that fluid coming back in because when we get to the venous end, my hydrostatic pressure has changed. My osmotic pressure has not. My osmotic pressure is exactly the same. It's still 20 millimeters of mercury. I still have the same number of solutes trying to push against that capillary wall. The only difference now is that my hydrostatic pressure has shifted, so that now I end up with 13 minus 20, which is actually a negative 7. So I get a negative net filtration pressure, which basically means that water and fluid will move back into the capillary. You guys following me? All you need to remember is hydrostatic minus, good grief, come on, Judy. Try this again. Hydrostatic minus osmotic equals net filtration pressure. If it's positive, water moves in. Did it again. Water moves out. It's positive, water moves out. If it's negative, water in. That's all you need to remember. You with me? Yeah? Okay. Questions here? So this is where we talk about skeletal muscle pump. Questions?
Can you explain how sympathetic stimulation influences that?
So sympathetic, how it influences what?
Venous tone.
Okay, so venous tone is basically a contraction of a vein, right? The continuous contraction of a vein. Okay? The sympathetic nervous system is going to increase your heart rate, right? That's your fight or flight system. So it's going to keep those veins a little bit tighter and help that blood move a little bit faster to get it back to the heart. Does that make sense?
Yeah, that makes sense.
Okay. Other questions? Okay. So here's what I want for your participation question. I want you to give me the arrangement of vessels from largest to smallest to largest. So starting at the aorta and ending at the vena cavas. We did this way back at the beginning. And then I want you to tell me what your understandings are of relationships between pressure and volume in relationship to those vein sizes. As those veins get smaller, what do you expect to happen in terms of the pressure of the blood and in terms of the amount of those vessels that are the cross-sectional area of those vessels? Okay? Got it? If you have questions, I can hang out for like another minute or so. My dog is about to lose his mind. If not, I will see you guys on Wednesday. Simon just typed the question in the chat if you missed it. Oh, my mouse doesn't work. I need to go put the... I know, Spencer. Hang on.